Hey guys, in this video we're going to talk about the stream function, the potential function, and how when these two combine with Laplace equation will give us the first step in simulating flow around objects. These two concepts are very important in fundamental aerodynamics course, and it kind of really changed the way people approach the subject. These concepts are relatively old. As you can see, it was developed by the concept of velocity, potential, and stream function was developed by Joseph Lagrange in 1788, and then Laplace, the year later, came up with the Laplace equation, which is considered as the governing equation for incompressible inviscid rotational flows. Right. So in this video, we're going to talk about what made these two or these three concepts so important that it allowed us to create flow over objects or different shaped objects. Okay, all right. So, well, you basically asked the question that Lagrange asked back in the day. How can I simulate flow over different shaped objects? So we discussed a little bit about this in the class. Basically, the gist of it is that in order for us to represent flows, we'll start with just two-dimensional flow field, right? So that means you have x and y. So that means flow over an object can be represented as a series of lines and curves. And we already saw equations for streamlines, straight lines, and path lines. And even if not streamlines, straight lines, and path lines, we know how to represent a line or a curve in a 2D space, right? So all we have to do is figure out a way to map that flow or those curves and lines around a shape that is given in this slide, and from there back out velocity and pressure. So in class we discussed these three different questions, and I hope you got an understanding of the thought process these guys went through back in the day without computers, without any sort of modern technologies. They just relied on pure math and intuition, which is pretty cool. All right. So let's start with the stream function, try to understand what that is. In your homework too, you simulated, well, you kind of determined the streamline for this given flow field. U equals x squared y and v equals minus xy squared. If you remember what the equation of streamline was, that was, I think it's like xy equals x naught times y naught. But before that, I want you guys to look at the handout that I gave in class. Mainly because as we go through this slide, I want you guys to write down and fill out the guided notes as you go along, so that you are not just watching the slides, you're also working alongside as we do in class. Okay, so it's very important that you do that, because you really need to understand how these equations connect to each other and how they are derived. Otherwise, you'll just be watching the video without having any context. So I strongly recommend having that handout next to you. So the handout I'm talking about is this handout called stream function and velocity potential Laplace functions that I gave out in class. Okay, so in fact, what you can do is that before even watching all of this video, pause here and then try to go through the handout and see if you can fill in some of the equations. And then once you've gone through it, come back and watch the video, right? So that you can make sure that you did things right and you were able to follow along. Okay, so all right, let's get to it. Again, make sure to have the handout. Right, so the equation of the streamline is basically xy equals x naught and x naught times y naught, and that's pretty much what you got from the second homework, I believe. This is the streamline, straight line, path line for this given flow field. So as you can see, the streamlines are curving, and the streamline is basically tangent to the velocity vectors. This is actually great, and for a given x naught and y naught, which is the value at which you want the streamline to pass through, you'll get, programming this equation, you get a streamline, right? But, if you want the streamline in the entire flow field, what do you have to do? right? So you have to put in every single x naught and y naught in the 2D space to actually make the streamlines go through every single point in this 2D space, right? Which turns to be a tedious task if you're looking at, a complex flow field, right? So let's try to condense this and find a way to represent the entire flow field all at once, okay? Now I'm going to represent, in the left hand side, you can see that that is a function of x and y. Right here in this equation is just x times y, but it could be any function of x and y. On the right hand side, as you can see, x naught and y naught are constants. So I'm going to represent that as just c. And when you replace this with the fancy Greek letter psi, that's pretty much what the stream function is. Okay, so it's a property which represents a fluid flow or streamlines in 2D space. It's a function which represents a flow field in 2D space. Okay, that's all there is to it. Now, let's put some. Let me go back and make sure to animate this as well. So that there's good progression. So basically, what we're trying to do here is trying to look at what stream function really is and how we can attach some validity or physical reasoning behind this property. Right. So consider two streamlines, C1 and C2, and you have a velocity that's going in between, and these two streamlines are separated by delta n. Okay. So basically, this is a very important aspect of stream function because this is the step where we connect the conservation of mass to the concept of stream function. Okay, so as you see and as we go along, you'll see that that's pretty much all there is to it for stream function. Stream function, what it really means is that it's a concept that is developed around conservation of mass. Okay, so imagine, just consider that there are two streamlines with two different constants separated by a distance delta n. So if we were to quantify the mass flow in between these two streamlines, how do you write it? So I hope you actually gone through the handout and trying to formulate the equations here. But if not, it's basically rho VA, right? So mass flow rate is basically density times velocity times delta n. That's how much mass flow is going through this distance. Now rearranging this, we can get that the change in stream function divided by change in the normal distance equals rho v. So now when the limit n goes to 0, right, this becomes a partial. So that means you can take the stream function, differentiate with respect to the normal direction, and you can actually get the product of density times velocity, which in itself is pretty cool because this is the first time we connected the stream function to a velocity, right? So again, remember what the goal here is, right? Our goal here is to predict the velocity information in a given flow field, right? Because if you can figure out the velocity, you can back out, pressure, and you can back out forces. So this velocity is a holy grail for all aerodynamic measurements. Okay, so and we, for the first time, we connected that to this concept called stream function. Okay, it's pretty cool. Now that's why this stream function is revered, because it gives us a way to predict the velocities, right? So, but we need to put this in XY space, right, in a 2D space. So let's do that in this, in this step, right? So all we're trying to do here is that divide that delta n in terms of delta y and delta x. All we're trying to see here is that can we divide that mass flow rate coming through delta n in terms of mass flow rate coming from delta y and delta x, okay? So again, keep in mind that the velocity in x direction is u and the velocity in y direction is v. Since the x direction is towards left, we consider that as a negative x, right? So, all right. Now we can represent this rho v delta n as rho v delta x plus delta y. Make sure to add a negative sign in here. So let me go ahead and actually do that. So there you go. So that's negative delta x. The reason is because again, you go up positive is up, and then towards left is, or opposite velocity is negative right there. All right. So again, approach the limit. You just basically condense this down to rho u times dy minus rho v times dx, because velocity in x is u, velocity in y direction is v, right? So, and we know that for any given 2D multivariable function, using chain rule of calculus, we can differentiate them as the following, right? d psi is dou psi by dou x times dx plus dou psi by dou y times dy. Now, basically all you're trying to do is compare these two equations, right? Just compare these two equations, and then you basically get rho u equals dou psi by dou y and minus rho v equals dou psi by dou x. Now, again, if you consider incompressible flow, you can bring the rho into the stream function, which means it's basically a constant. Then u just becomes dou psi by dou y, and v becomes minus dou psi by dou x. So again, for the first time, we connected the stream function, the concept of stream function, to the actual velocity component, which is, again, it's pretty cool, right? Because it provides us a way to represent a flow field in a 2D space, right? So now let's try to find stream function for these two velocity components, x squared y and v equals minus x squared. So when you do that, here is, this is basically the flow fields, straight line, path line. So I hope you guys were able to calculate the stream function for this, which means, in the end, you just end up getting x squared y squared by 2. Now, if you were to plot this, imagine what you get. You will get something like that. Now, you can see the general trend of flow field, right? That's actually, showing that it's curved. But one other information it shows you, it also is that the magnitude. So what do you think this legend represents? As you know, these are basically the function of stream, the values of the stream function. And what did this represent? Think about it, right? So the concept of stream function is actually derived from conservation of mass, or mass flow rate, right? So that means as you go from this corner 0, 0, diagonally over here, you can see that the velocity vectors are increasing in magnitude, right? So, and that's the exact information that you actually get out of the stream function. So you not only get the information of the flow field, you also get the information of how the velocity is changing in a given flow field. And now that's pretty powerful for just this one simple function, right? That's why people like stream function a lot. It does two things, right? Gives you the idea of flow field and gives you gives you an idea of where the velocity is increasing. So that's stream function. You will be using this stream function a lot to, in the future, in the next homework. So I like to share the code that I wrote to actually plot these. Here this is just a contour graph, right? But you can actually visualize the individual streamlines, right? Again, another benefit of using stream function is that you don't have to plot each and every streamline by changing the x naught and y naught. You'll get the entire flow field. And when you plot it this way, you can literally see the flow lines, the streamlines, sorry. And watch what happens to the distance between the streamlines right here, right? The distance between the streamlines reduces as you go from this corner, in the diagonal direction. So that can only mean that the velocity is increasing, right? And that's what you show here in the vector plot, right? So again, I want you guys to really think about and really understand the different information that this just one simple function can tell you, okay? So in polar coordinates, sometimes we like to work with polar coordinates. So just note down this formula. It's V r is 1 by r, dou psi by dou theta, V theta is minus dou psi by dou r, right? All right, moving on to a next function called potential function. So people like to work either with the stream function or potential function. I personally like stream function because I can literally see the flow field using this function. But there are some instances, especially when we deal with panel methods, where we like to use potential function because potential function is nothing but gradients of velocity, right? Let's understand what that means, okay? So again, as you know, we talked about vorticity in the class, right? Vorticity is basically gradients or curl of velocity vector, and for irrotational flow, that's equal to 0, right? Now consider a vector identity. If psi, this function, is a scalar, then any gradient of the scale, or any curl of the scalar function equals 0, right? So that means that just by comparison, we can see that the velocity vector equals gradient of psi, a scalar quantity, right? So expanding that, all that means is that dou psi by dou x equals u, dou psi by dou y equals v, dou psi by dou w equals w, right? So that means you can represent the flow field by either quantifying the stream function or by quantifying the velocity function, right? So that means, right, if you either get the stream function or the velocity function, you know u, v, and you can calculate u, v, and w, which are basically gradients in the x, y, and z, okay? So that should be a z, not w. X, oh, no, yeah, there you go, x, y, z. There you go, right? So this, you know, the entire concept is basically built on just that. You know, there is a scalar function that you can represent the velocity gradients as. Okay, so that's pretty much what the potential function is. Pretty easy, right? Moving on to a Laplace equation. So the stream function and potential function by itself, even though they tell a lot of good information about the velocity, it will be practically useless without, you know, applying that to, you know, a flow field and using that to create flow around different objects. And in order to do that, we really need this, what is called the Laplace equation, right? Now, let's try to understand what this Laplace equation is. Okay, an irrotational flow in 2 dimensions can be represented as, right, dv by dx minus dou u by dou y equals 0. This is basically, again, vorticity, right? Irrotational, that's irrotational flow. So from the stream function, we know that u equals dou psi by dou y, v equals minus dou psi by dou x. So go ahead and plug that in. You get, you know, that, and simplifying, you get something like this, right? The second order derivative of stream function with respect to y, expect x and y, and the addition of that goes to 0. So there is a name for this, is called the Laplacian. So that means Laplacian is basically a second order derivative of a given function, right? So that means dou square by dou x square plus dou square by dou y square of the stream function goes to 0, right? So there's a bar. So, okay, what's so special about this equation, and why, you know, what does it even mean? All right, and what does this tell us? All right, let's try to, you know, understand and dive a little bit more deeper into what this equation is and, you know, what it represents. Okay, all right. So you can write the Laplacian, this term right here, as the divergence of the gradient, because that's what really is, right? If you really look at Laplacian, it's basically del dot del psi, right? So you're taking a divergence of the gradient of the stream function, right? So, and you know that the gradient of stream function is basically the velocity vectors, right? Now let's put it that way. So this, when you apply gradient of the stream function, you just get dou psi by dou x plus dou psi by dou y, right? And then dou psi by dou x, we saw that it's basically negative u, or negative v, right? And dou psi by dou y is just u. Now, when you know, again, use the vector identity, and del dot minus v plus u is the same as minus del dot v plus del dot u. Now, expanding this, again, divergence, right? So dou v by dou x plus dou v dou y equals dou u dou x plus dou u dou y. Now I'm going to rearrange this. So if I rearrange this right here, on the left-hand side, I get a rotationality condition, right? It says dou v by dou x minus dou u dou y equals, I can write the same as, on the right hand side as dou u dou x plus, dou v dou y. Just bring the negative sign inside, right? So as you know, for irrotationality condition, dou v by dou x minus dou u dou y should be equal to 0. And the only way, the equation holds is when the right hand side is also equal to 0, and which it is, right? The right hand side is basically the conservation of mass. Okay, so all Laplace equation tells you is that, hey, the flow is irrotational and it also satisfies conservation of mass. Okay, so that is why Laplace equation can be used to represent an inviscid irrotational, incompressible flow around a given object, right? But still, this kind of shows us what Laplace equation is, what its components are. But at the same time, in terms of application, we got to look at, okay, how is this can be useful, right? Now, in order to understand the question, we got to look at the nature of the Laplace equation itself, and that nature is why this equation is considered as the most famous equation in aerodynamics. Okay, it's a second order linear partial differential equation. What that means is that, again, this is a second order partial differential equation, and it's also elliptic in nature. Okay, now it's not that complicated to understand this equation, and you will see why it's linear. Okay, now take for example f double prime of x. That's basically the second order derivative of string function equal to 0. Now if you were to integrate that, right, just once, you will get dou psi by dou x, which is the first derivative of psi equals to a constant. Now if you were to integrate that again one more time, you will basically get this, right? And you guys know what this is an equation of, right? This is basically an equation of a line, which is linear. So that's why it's, people like Laplace equation, because the solutions are always linear. But now you may think, does that mean a curve cannot be a solution of Laplace equation? Well, let's find out, right? So let's take this function, which is again clearly a nonlinear function, right? So say its string function is e power x times sine of y. Now let's take a first derivative of that. You get that. And when you take the second derivative of the same function, guess what you'll get? You'll actually get 0. So there are some equations, even nonlinear equations, which satisfies Laplace equation, right? So that's why, if you find some solutions of Laplace equations, then they can be thought of as the flow fields, which are potential and irrotational. And all potential irrotational flow field will be governed by this Laplace equation, which generally means that all potential irrotational flows or satisfy conservation of mass, right? So, all right, now here is the beauty of Laplace equation or solutions to Laplace equation, right? Let's watch what happens. You have these, these two solutions. We know that this function right here is a solution of Laplace equation because the second order derivative is 0, and this function is also a solution of Laplace equation, again because the second order derivative is 0. Now I'm going to simply add it up, right? I'm just going to add, straight away, right? And I'm going to see if this addition is a solution of Laplace equation. Now take the first order derivative, right? And then I take the second order derivative, and guess what? I end up getting 0. So that means you can take individual solutions of Laplace equation, you can add them up, and the net result will also be a solution. Net result will also be a solution of Laplace equation, which is pretty great, right? Remember what we talked about initially? If we want to, simulate flow field around a given condition, around a given object, that means I can take, a flow that is basically, I'm going to draw right here. right? I can represent a flow field this way, right? This is the flow field. Plus, I can say there is a curve right there. Now, if I can find that these two are solutions of Laplace equation, then I can simply add them up. And the result will also be a solution of Laplace equation, which is pretty cool, right? Now, let's put this to test, right? So, you have the free stream, right? And that is basically, I can represent that as v infinity times y. So, at every point I change y, and at every point my y will have the value of v infinity, right? So now if I want to simulate flow around a cylinder, and the equation of the cylinder is like, for example, if we were to represent this as a stream function or a streamline, it's x squared plus y squared, right? X squared plus y squared equals r squared is basically the equation of a circle. Now, can we add them up and get a, some sort of graphical representation of flow around the cylinder? We cannot, right? And you guys can probably guess why that is, because this is not a solution of Laplace equation, right? So if you take second order derivative of this equation, you probably know what you end up getting, right? When you take derivative of this, you get 2x squared, and then, well, you'll get what, 2 times x, and then take a second derivative of that, you just get 2, and then you get 2 over here, so your answer will be 4. So again, as you can see, it's not 0, right? So we cannot simply add them up. Now, this presented a big hindrance back in the day, so people thought, now what do we do, right? Now, the whole idea behind stream function, Laplace, and in a potential function is that so that we can represent flow field in a 2D space, but not all geometries can obey Laplace equation, right? So that's when people came up with what is called elementary flows. Okay, let's make up some mathematical flows which we know obeys Laplace equation, and if we add them up, maybe we can get something similar to a cylinder, or something similar to an airfoil, something similar to a bullet, something similar to any shape that you want. Okay, that's what we're going to talk in the next video. All right, see you in the next video.